Okay, so we have shown an upper bound on the extremal number of complete bipartite graph. And now we want to talk about extremal problem for hypergraph. Here, when we are discussing about extremal number, so here we were more focused on its exponent. So what is the right exponent? And we were not really giving much attention on the implicit constant that we get here. On the other hand, in Turan theorem, we have a more precise result. So in particular, this gives us the roughly this number of edges with a small additional term. We can actually compute this as this number. So if you want to aim for more precise result here, this constant is important. So in general, we give a name to this constant. For say H is on R graph with alpha times n choose R edges. And that this H has density alpha. And therefore on higher graph F, we let high F be we want to denote pi F as this constant. So what constant we get here? And in order to forget about this like smaller order term, we use the following way of taking limit. It's if you compute the extremal number of F and then divide it by n choose R, and let n goes to infinity, then what number we get? So that's the constant in front of the major term of the polynomial that we get there. And we call it the Turan density. Sometimes it's called Turan density, sometimes it's called extremal density, but we write it using this pi notation. Okay. Then what? Once we define certain parameter, we have to show that this actually is well defined. So we can actually show that this exists. For any R graph, we know that its Turan density exists. And what? How do we show it? Once we want to show limit exists, there are several techniques. One of them is that if you have a sequence which is bounded from above and bounded from below, and monotone. Okay, let me put it this way. If you have a sequence which is monotonely non-increasing, so decreasing, and its it's bounded from below, then it must have a limit. So we want to show that. Then what? We want to show that this is bounded from below by 0. So it's never non-empty. I mean, non-negative. This is non-negative number. So as long as we show that this is decreasing, it's enough. So we want to show this one. For that, how do we do it? So we suppose that we have a graph H which achieved this. H is an M vertex R graph. With the alpha times enters the R edges that has no copy of F. Then what? If we choose one vertex at random and delete it, if we randomly delete the vertex to obtain an R graph H prime, then what do we know? The expected number of edges of H prime, we can compute it. Which is what? So you have some edges, and for specific edge E, what's the probability that it's deleted? If one of its R vertices is chosen, then this disappears. Otherwise, it survives. So the probability that it survives is 1 minus R over N, and that holds for all its edges. So by linearity of expectation, the expectation is this. And what's this? Using the formula, that's N choose R, and this is what? N minus R choose N. This is N factorial R factorial N minus R factorial. You use this, this one term cancels out, and this is exactly alpha times N minus 1 choose R. And what do you know? If expectation is this, means that there must be a choice. There exists a choice of vertex in H such that H minus P, if it has density at least alpha. Expectation is alpha, so there must be a vertex which does as good as this expectation. So we can find a vertex with deletion leaves graph with density with alpha. Moreover, if H prime is a subgraph of H, so it does not contain F as a subgraph. So what does it mean? That means there exists an N minus 1 vertex graph with alpha times N minus 1 choose R edges having no copies of F. So reject this. Thus, this shows that this is alpha and what this is bigger than alpha. So we actually show that this is non-increasing. Thus, what this sequence forms non-increasing sequence of real non-negative number. Okay. So now we know this. Then, for example, for this graph, so before we show that Kobayashi-Turan theorem says that, for example, if you have a KSS, then that has limit 0, is Turan dash 0 because what? It was at most big O went to the 2 minus 1 over x. So as n goes to infinity, if you divide by n to 2, then it goes to 0. And using that, we can prove further, statement about other hypergraphs. Okay, maybe before discussing that, this implies that for all bipartite graph, hierarchy is 0. Because any bipartite graph is subgraph of certain complete bipartite graph. So we know this. And moreover, we can show that the converse also holds. F is a bipartite graph, even only if converse is 0. Because F is not bipartite, then what? And it's not a subgraph of complete bipartite graph. So you can consider balanced complete bipartite graph, which has density one half. So non-bipartite graph implies that this is at least half. So what does this mean? This means that there are no graph F whose density is between 0 and half. Whose Turan density is between 0 and half. Furthermore, we will, the Simonovich theorem that we learned in the introduction to the graph theory course. We will learn about it again, so this will come out later in the course. But this shows that for any graph, this is what? Either half, 0, half, 2/3, 3/4. So this is the form of this. Let's write it as yeah. So this takes values inside of here for graph. Okay, then one of the natural question is that can you prove the similar thing for hypergraph? So for example, we have these. Anyway, prove such a thing for hypergraph. For hypergraph, let's say we say that the r-partite, let's say on R graph is k-partite if what? There exists a partition P1 to Pk of the hypergraph. Let's say hypergraph is H. Such that each H intersect each set Pi and most once. So each H uses at most one vertex from each part. And it is a k-partite. And generalizing this, Erdős in 1971 proved that there are no hypergraph F. He proved that this is zero if F is R graph, R-type R graph. So both direction holds. So this direction is quite easy. Same as before, you take a complete r-partite graph. If F is not r-partite, then it's not a subgraph of this. But this has positive density, so you get this direction, and the other direction is not trivial, but that's also holds. We will prove this. So before proving this, maybe let's discuss a bit about the generalization of this to hypergraph. So for graph, we know that the exactly one number can be the Turan density of certain graph. Then for hypergraph, what happens? So to describe, okay, the answer is that for hypergraph, we don't really know the full picture. But for example, here, but this forms this is quite discrete. You have this number, there's nothing between, this nothing between, nothing between. And for hypergraph, is it also the case? Motivated from this question, we say that some number between 0 and 1 is a jump. We call it a jump for an integer r if the following holds. So what? So here, after half, there are this interval of like nothingness here. So there are no hypergraph whose density is here until you have this one. So there is this gap. So we want to describe this gap. So if there exists, say, some C, such that for any, say, epsilon and T, any sufficiently large M vertex R graph with alpha plus epsilon times n choose R edges contain some T vertex subgraph. This many edges. So, so at first look, I mean, this seemed a bit different from saying that there are this gap, but this is essentially equivalent. This is equivalent. For graph case, what does it say? For graph case, so what does it say is that if you have more than half, your density is more than half. So if you have half plus epsilon times n choose 2, then you have what? You have a K3 in your graph G. But what's this K3? K3 has 3 vertex and it has more than half plus half. This many edges. So this density was like a bit over half. But suddenly you have a subgraph whose density is a lot higher than half. So that's what's described here. So if this alpha is a jump, then what happens is that if you have a, say, certain f whose extremal number is, I mean, it cannot be a bit over alpha, because if there is a f-free graph with this many edges, then what? You have a subgraph with this many edges. And then this n and t are related, so that if t is already fixed right here, and as long as n is sufficiently large, then you get it, right? Then you take t being very large, and then n is much larger. And you know that if there is this thing, then naturally you find the subgraph with this many edges. Okay, but this is subgraph of the original one. So this is again f-free. It doesn't contain f as a subgraph. And then t is large, so this said this is what? Bigger than alpha plus c t times t to the r. So by taking this, by increasing this t, it shows that its limit of this Turan density is bigger than alpha plus c. So it shows that if there is a f-free graph with more than this many edges, then there must be a f-free graph with more than this many edges with t vertices. So this shows that there are no graph f whose Turan density is between alpha and alpha plus c. It cannot be. If such a graph exists, then obviously by using that, its Turan density is actually bigger than alpha plus c. So this is the right way to define this jump. And this shows that every alpha between 0 and 1 is a jump for two graph. For graph. Wherever you start, there you can find the small interval. There are no Turan densities there. And all this show that all numbers in 0 and r factorial over r to the r are jump. I mean, more precisely, he proved that not only he proved this, but also he proved that there are no graphs, no R graph with Turan density in this interval. And there is conjecture that you consider that every number between 0 and 1 is a jump for all RL3, but Frankel and Roder in 1984 disproved this. And they find the sequence of values of non-jump for all RL3. So that was a bit of history. And we can prove this LGC theorem that for R and S at least 2 and N at least say S square, we have that the extremal number of N K S S S r-partite R graph is almost S times N to the R minus 1 over R S to the R minus 1. So here we write K to the bracket R. This denotes the uniformity. This is R graph. And this is the r-partite R graph with the S parts. I mean, the R parts of side F. If we know this, then we immediately get this statement. And by considering also one direction, is that you consider the r-partite R graph, which are complete. There, I mean, using this example, this direction is obtained, and the other direction is from the previous theorem. And then if you know that, then this statement is also easily deduced. Okay, so let's prove this. We use induction on R. And base case, R equal 2, we already know. We already have proved the extreme number, upper bound on the extreme number of K to 2, and that can be easily generalized to KFL by showing that, I mean, so in this case it's 1, 2, yeah. R is at least 3, and we know that the external number of n K to the R minus 1 uniform, R minus 1 graph with the partite F is what? Assume that this holds. What do we do? We want to generalize the argument of counting K12. So before we count K12, and in general, K1S, we find many of them, and then we choose the one which use the same end vertices here. We collect them to obtain K1S. And we now want to generalize it, but now we have a R uniform hypergraph. And what we do is we want to find F vertices which altogether share, let's say, this two, this two, this two, this two. So this structure. Correctly, these two are shared by them. So there is this edge, this edge, this edge, this edge. And you have this. In the same way, you have this if this edge, this edge, this edge, this edge. You keep do that, and you collect many of these pairs. And then if you find, say, this in here, and if you know that this is an edge, and this is an edge, this is an edge, this is an edge, and so on, then you find the K222. That give you a 3 uniform 222. So we will generate this idea. So we collect many pairs, and then in the pair, we reduce the problem of finding graph instead of hypergraph. So we lower the uniformity. For that, let H be on R graph with more than n to the s times n to the r minus 1 over SGR minus 1 H on a vertex at P. And what? We consider auxiliary bipartite graph. G on with the bipartition A union B, where A is same with the vertex set of H. And B is collection of R minus 1 tuple, R minus 1 subset of B. Let's simply write P. So, and in this G, we put an H between A and B, with A in this capital A and B in B, if and only if but their union is an H in H. So we are doing this. So this one vertex and two, if they form a 3 uniform H, then we put an H between this vertex and this pair. Then what? Then we have the added all degree of the vertices in A. So that's the number of edges between G. This is what? If you have a edge here, then they give you a edge between A, B, C, no, X, Y, G. And X, if give you X and Y, G, so this is Y and X, G. And G and X, Y. So you get 3 edges. In general, if you have a R uniform hypergraph, this give you R edges. So this is R times e to the number of edges. And that's bigger than R times S times N to the R minus 1 over S to the R minus 1. Now what we have, similarly as before, as we were counting K1, 2, now we count what? We count this structure. So for each, how do we count? For each B, so this is B, we count the A's. How do we do it? We count the degree to the we just count the, instead of choosing F from this degree, let's just count the every S tuple. that's easier for the calculation. And by using convexity of this function again, we have this. And what do we know? We know that this degree sum on the bipartite graph, this and this are the same. So that's what, bigger than Rs n to the R minus 1 over S to the R minus 1 divided by n to the R minus 1 F. How do we know? This is n to the R, and you do the calculation, then you can see that this is 2 times S times n to the R minus 1 plus S minus 1 over S to the R minus 2. You can verify this. On the other hand, what? So this is counting what? This counts, so we count all the S tuples of neighbors of vertex B. Hence, this one is what? Let's write. So we write when we write the neighborhood of a vertex, this is union of all vertex there, and then union of this neighborhood. And it's convenient to consider the intersection. So let's write n star of A, that's intersection of any vertex A, its neighborhood. You take the neighborhood of this vertex, and then you take the intersection. And we write, let's say, P1 to be at Pi. Yeah, so let's use this notation of n star. And what? This is exactly counting for its R minus 1 vertex. You choose neighbor, its possible neighbor, you choose S tuple. Well, possibly you might use the same vertex twice, but that's what it's counting. But from the perspective of these vertices, this is what? For this S tuple, you count the R minus 1 tuple, which forms a H with each one of them. So these two are counting the same thing. And the later one, there are actually two cases. We want to be S in A, and all of them are distinct. Some of them are not safe. So we have this. But what's this? This term is what? So this size is at most B, which is side n to the R minus 1. And the number of terms here, they're what? You choose S terms from A, but they are not all distinct. Two of them has to be same. So by choosing two terms that has to be same, and then you choose, let's say 1 to S, you say I and J are the same thing, then what you have to do? You choose 1, 2, dot, 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 S, the coordinate, the tuple, and then IJ, you choose the same thing, so you have to take the n to the F minus 1 choices. And each time, I mean, you choose a vertex in A, so to be specific, so this is almost that much. So what do you get? So you have the first part plus n most x choose n to the r minus 1 times n to the r minus 1. Sorry, this is not r minus 1, this is s minus 1. Sorry. And what do you get? So you have this lower bound. So this is 2 times s times n to the r minus 1 plus s minus 1 over x to the r minus 2. And you have this, so you subtract it. But what do you know? It's n to the s plus r minus 2 times s squared over r minus 1 factorial. And we assume that n is bigger than s squared. And what? You just subtract on both sides, you get the, you can show that this term is bigger than this. But what do you get? From here, so there exist distinct vertices, so S vertices B1 to BS, so with so here, the choice of here is at most n to the f. You divide by f, divide this number on the left side, then you get this many with the, let's try it this way. This condition. So summation is bigger than that, and then the number of term is at most n to the f. So one of them must be bigger than this divided by n to the f. So you have this. Then what? We consider r minus 1 graph h prime with whose edges are exactly the r minus 1 set, which lies in this common neighborhood. So that was our plan, right? So P1, P2, P3, and we take this if this is an edge, this is an edge, this is an edge. Then what? Because of this, induction hypothesis yields a copy for K to the r minus 1 as in H prime. This together with P1 to PS form a copy of desired r-partite R graph in the original hypergraph H. So there is a contradiction because what we assume that H does not contain a subgraph isomorphic to this. So this shows that the upper bound holds. Okay, so maybe I'll add a bit more comment. As I mentioned, understanding this Turan density for general R graph is not well understood. We know almost nothing. For example, one of the very easy case of this complete graph on 4 vertices, complete 3 uniform hypergraph on 4 vertices. So this is the one. In other words, this is sometimes called tetrahedron. So you consider all the triangles here on the tetrahedron as your hypergraph H. And this is that. And what's the Turan density of this? This is not known. In 1941, Turan conjecture that this is 5 or 9. So why 5 or 9? You take n minus 3 vertex, n minus 3 vertex, n minus 3 vertex. You take n vertices and you take a partition it will be into 3 parts. And you consider all the edges of this type and edges of this type. So all the edges which uses 1 vertex from each part, and all the edges which use 2 vertex from one part and then 1 vertex from the next part. So, for example, this is not included. This is not an edge. So there is this order, cyclic order. In that case, this is low tetrahedron here. Because if you choose 4 things, 4 vertices, there must be a one part which contains 2. Then this edge is there, but the other edge, this edge is not there. So you choose the previous one, and this is not an edge here, so it lacks an edge, so it doesn't contain tetrahedron. And then if you compute, then this gives you a lower bound. On the other hand, upper bound is not known. The best known upper bound is using something called flag algebra. That's some theoretical way to use computer computation to obtain the inequality. Anyway, so I will not discuss what it is, but using that, I mean, there are some upper bounds. This is developed by Razborov. It's something like 0.56 something. I mean, something like 0.56. I don't need to remember the exact upper bound. I mean, the best of known upper bound might be slightly better than this, but if it's 0.5555, right? It's slightly above, but this is not known. Okay, so we learned about Turan density of a hypergraph, and then we show that all r-partite R graph has Turan density 0. And if it's not the r-partite, then the Turan density, the natural example give you that its Turan density as elliptic. And in next video, we will learn about something called supersaturation, and we use that to deduce the Erydice-Stone-Simonovich theorem. Yeah, that's what we will do in the next video.